If you remember, in the first video of mine on the topic of modulation and demodulation, I had given you a general definition of modulation, and later when we started the topic of amplitude modulation, we went a little more specific on that, and I gave you the definition of amplitude modulation. But along with that, I had also mentioned the definitions for frequency modulation and phase modulation. I have picked up the same definition here for frequency modulation. So it is the process of changing the frequency of a high frequency carrier wave in accordance with the instantaneous voltage of low frequency message signal. So now, what exactly this definition means and how does the frequency of the signal, that is frequency of the carrier signal, varies depending on the amplitude of the message signal, that we will see through this diagram. So what you can see here is the first wave, what I have taken here, it is a high frequency carrier wave, and the second signal shown here is a message signal. Please observe, students, the message signal is a cos wave that I have taken here. In case of amplitude modulation, we had actually used a sine wave, whereas for frequency modulation, we will be using a cos wave here. So now, this low frequency message signal is represented as the second one, and the third signal, what you can see here, is the frequency modulated signal. If you observe carefully, at this region, you can see that the cycles are close by, indicating high frequency. At the same time, even in this region, you can see that the cycles are placed close by, indicating high frequency again. And in both these regions where you can see the high frequency of the FM signal, just observe the corresponding amplitude of the message signal. Here the message signal is at its positive peak. At the same time, for this also, if you observe, the positive peak is here for the message signal. At the same time, if you observe the cycles here in this region, you can see that the cycles are far apart as compared to this region. And here the frequency of the signal is lesser. And if you relate this with the message signal, you can see that here the message signal is at its negative peak. So that means as the amplitude of the message signal varies, accordingly the frequency of the FM signal varies. Now, students, I have copied the same diagram which I showed you previously onto the Paint app, and we will just look into a bit more in detail about how the FM signal has this particular pattern. I will just pick up some lines here to indicate the different time instance of all the three signals. For example, when I draw a line like this, what I intend to show you is the time instant of the carrier signal, the time instant of the message signal, and the corresponding time instant of the FM signal. Now, say for example, I talk about the time instant where the message signal is at zero amplitude. So when the message signal is having zero amplitude, that time what happens is whatever is the carrier frequency, the same carrier frequency signal will be observed here at the FM signal. So now say for example, I will take up the carrier signal as 10 megahertz. So at that time, what happens is the signal amplitude at this point here at the message signal, you can see that the signal amplitude here is almost zero. And since I have taken the carrier signal as 10 megahertz, the same signal frequency will be reflecting here. That means the FM signal will also have almost the same frequency as 10 megahertz. Now let's look at a different time instant wherein, if you see, I have placed the vertical pink line here at this point where again the signal amplitude of the message signal, it is zero. So at this point again, as the amplitude of the message signal is almost zero, the frequency of the frequency modulated signal will be again nothing but roughly equal to or almost equal to that of the carrier signal. Now let's consider another time instant little ahead from the zero amplitude, say at this point. So when the message signal is having this much of amplitude, if you observe from the previous condition, that is when it was at the earlier condition, we took the amplitude to be something 0, and for that the corresponding frequency was 10 megahertz. So now here if you observe, the amplitude of the message signal is slightly increased. Accordingly, the frequency of the FM signal here would have slightly increased to a value which is little greater than 10 megahertz, say maybe 10.1 megahertz or 10.2 megahertz, something like that. Now, as we move to the next time instance, say somewhere here, the amplitude of the message signal is further increased, and accordingly the frequency of the FM signal, if you observe in this region where the cursor is highlighted, so in this region if you observe, the frequency of the FM signal is further increased. And just keep observing what happens as I reach to the positive peak. So now here I have placed the line exactly at the positive peak of the message signal, and at the corresponding location on the FM signal, what you observe is that the frequency of the signal here is at its maximum. The amplitude of the message signal is at its maximum, and corresponding frequency of the FM signal is also at its maximum. So now let's take another time instant wherein the amplitude is decreasing when compared to that of the previous condition. The previous condition was at the positive peak. Now we are considering the next value wherein the amplitude is little lesser than the positive peak. So at this time instant, if you observe for the corresponding FM signal, you see that the frequency here is slightly reduced as compared to this condition. Here we saw that there was the maximum possible frequency, whereas in the current situation, that is where the pink line is highlighted, here you now observe that the frequency is slightly decreased. Now we come to another time instant where the amplitude of the message signal is 0. So here what happens is, as explained earlier, the frequency of the FM signal will be nothing but equal to that of the carrier signal. So it will be nothing but at 10 megahertz. Now, moving ahead to the negative half cycle of the message signal. So here you see that the amplitude of the message signal is on the negative side. So what happens is the corresponding frequency of the FM signal will be slightly lesser than 10 megahertz. 10 megahertz is the frequency when the amplitude is 0, but here the frequency is slightly lesser than 10 megahertz. And as I move ahead, see at this time instant, the amplitude is further decreased. So that means the frequency of the FM signal is also further decreased. And this continues till I reach the negative peak. Now here I have reached the negative peak. So here at the negative peak, what happens is the frequency of the FM signal will be at its minimum. Observe, when we had spoken about the positive peak, the corresponding frequency of the FM signal was at its maximum, and now for the negative peak, the corresponding FM signal frequency is at its minimum. So like this, depending on how the amplitude of the message signal varies, accordingly the frequency of the FM signal is varying. Now as I move this line a little more ahead here, you see that as compared to the previous condition of the negative peak, now the amplitude is slightly lesser when compared to the maximum negative peak amplitude. So that means here now the frequency of the FM signal will be slightly greater than that what it was at the negative peak. So like this, depending on the variation in the amplitude of the message signal, accordingly there will be variation in the frequency of the FM signal. Hoping that now you have clearly understood how the frequency of the FM signal varies depending on the amplitude of the message signal. We move on ahead in this discussion. Now we will name, or we will give the representation of these waveforms in the form of equation. So as we followed in the signal representations for AM, similarly we use the same terms here for FM also. C is the subscript given in this equation indicating that it is for the carrier signal. So the carrier signal is represented as Vc of t is equal to Vc sine omega ct, where Vc is nothing but the amplitude of the carrier signal and omega c is the angular frequency of the carrier signal, which is equal to 2 pi fc. Fc is the frequency of the carrier signal. The message signal is represented as Vm of t, m being the subscript indicating that it is a message signal. So Vm of t is equal to Vm cos omega mt, where again Vm is the amplitude of the message signal and omega m is the angular frequency of the message signal, given as omega m is equal to 2 pi fm, where fm is nothing but the modulating or the message signal frequency. Moving on to the third signal, that is FM signal, the representation is as Vfm of t is equal to Vc sine theta of t. Now here Vc is of course the amplitude of the FM signal. If you observe throughout the signal for all the different time instants, observe the cursor movement. For all these time instants, if you observe, the amplitude of the signal is constant and it is equal to the carrier amplitude. So that is the reason we have taken this as Vc, and the complete expression is Vc sine theta of t, where theta of t is nothing but the representation for the angular frequency of the FM signal. Now here, if you observe, the frequency of FM signal is not constant, but it is continuously varying. So for that reason, as of now, we have just mentioned the angular frequency as theta of t, and what exactly is this theta of t, that we will see at a later stage. Coming back to the diagram, here, as already told to you people, when the amplitude of the message signal is at its maximum, the frequency of the FM signal reaches to its maximum. That means the frequency here can be represented as the carrier frequency plus some extra frequency, which say I will represent it as delta FC. So this maximum frequency, I can represent it as the carrier frequency plus delta Fc, that is change in the carrier frequency. Similarly, when I talk about the amplitude at the negative peak, as I already told you, the FM signal frequency will be at its minimum. So when the frequency here is minimum, that frequency is represented as F min equal to the carrier frequency minus the change in the carrier frequency, that is Fc minus delta Fc. Always remember, whatever is the amplitude at the positive peak here, I have taken the same amplitude here for the negative peak. I have already told that this is nothing but a cos wave. So the amplitudes are nothing but at both the negative and the positive peak, the amplitudes are always equal. So that means whatever amount of frequency of the FM signal at the positive peak of the message signal has increased, by the same amount at the negative peak of the message signal, the frequency would have decreased. I repeat again, at the positive peak, whatever is the increase in the FM signal frequency, the same corresponding value of decrease in the FM signal frequency will be observed at the negative peak. So for this reason, the Fmax is represented by addition of delta Fc, whereas the minimum frequency, that is Fmin, is represented by subtracting the delta Fc value. Now, from this particular signal, we can make out that there is a maximum frequency which we have represented by Fmax and a minimum frequency which we have represented by Fmin. And the overall frequency modulated signal swings between these two values. That is, the frequency modulated signal swings between the Fmax value and the Fmin value. This overall swing is known as carrier swing and is given as the difference between this Fmax and Fmin. That is nothing but Fc plus delta Fc minus of Fc minus delta Fc. So if you simplify this representation or equation, what you get is the value, that is carrier swing, equal to 2 delta Fc. Alternatively, there is another formula for carrier swing, that is Fmax minus Fmin. So these are the two formula that we are discussing today for the carrier swing. One, carrier swing is equal to 2 times delta Fc, and the second one is carrier swing equal to Fmax minus Fmin. With this, we come to the end of today's video session. In the next session, we will be starting with the derivation of FM equation. So students, till then, take care. Bye-bye.